All right, let's open up to page 69. We're going to pick up where we left off yesterday, talking about these composition functions. So yesterday we spent most of the class just looking at values, like if you're going to plug in the number 2 or the number -3, okay, how we can use function values to kind of create something new. It wasn't until the end of class that we briefly talked about expressions, how instead of plugging in a number, we can start to plug in some variables, okay, something a little bit more advanced than just a number. And I think we did the first one, is that right? Yeah, we need to do the second one? Okay, so let's just try this next one on the right-hand side just for practice, and then we're going to get into some, in my opinion, some more advanced ones towards the bottom of that page. So if you take a look at the second one here, we got to think about what is this notation asking us to do. If you look at the first part, f of x minus 2, notice how that x minus 2 is inside the parentheses. It's representing an input, something you plug into the equation. So when you look at the f equation, we're going to take the time and plug in x minus 2 for both of those x values. And just like you would normally use parentheses when you plug in a number, we'll do the same thing when we're plugging in an expression. Okay, we're going to plug in x minus 2 for all the x's. It then goes on to say that we want to subtract g of 2x. So when you look at the g equation, we need to plug in 2x in for its variable. Now, if you're subtracting the g equation, you really should think about subtracting the whole thing, meaning every single term. So we technically should think about putting it in parentheses because you're subtracting all of it. So we'd have 5 minus 2 times, and then we'll plug in the 2x, and we still have the minus 3. So it looks like a lot, okay? It's a simple notation to start with, but what it actually means turns into something a little bit more complicated. Okay, not difficult, just complicated. From here, we're just going to use some algebra techniques like factoring, distributing, combining like terms, anything like that to help us simplify it down a little bit better. So if we first start off with the first term, we have a power of 2, which means you can write it twice and go through that FOIL process. Some of you might actually have to write it out. Some of us might actually be able to do it in our heads. Okay, more power to you. But if you were to write this twice and go through FOIL, let's see, we'd have firsts, outsides, insides, and then lasts. All right, let's continue through. So we can then encounter the next term. We can distribute in the minus. We then get to the plus 3. And next we have this big parenthesis grouping, but notice how there's parentheses within inside of that. So if you think about your order of operations, parentheses come first, but you got to kind of work on or from inside out, kind of like a layering effect here. So let's perhaps distribute in the -2 on the inside. So -4x and then a plus 6. So we did some distribution, okay, but we definitely have parentheses left, so we might have to do more. Let's go ahead and work our way through again. So we can distribute in the 2. And then for the last one, we can distribute in the negative or the minus. Again, bless you. There's more than one way you can approach these, if you will. Some of you might prefer to combine like terms as you work through it. Okay, that's definitely okay. I didn't really combine anything because personally, I like to wait till the end. That way I see everything that I have. So now that I have all the parentheses gone, I can start to combine some like terms to see what we have left. So when I look at it, I only have a 2x squared. No other squared term is there. We do have quite a few x's. We have negative 4x, another negative 4x, bless you, a negative x, and then a positive 4x. So if you combined all those together, we'd be left with negative 5. And then taking a look at the numbers, we have an 8, a 2, a 3, bless you. All right, so we're up to 13, minus 5, down to 8, and then minus 6, we're at 2. Okay, so after everything's combined, notice how it is a little simpler with what we have left. How are we doing with that? It's not numbers anymore like we had yesterday. Now we're working with expressions. Okay, a variable is left. We got it? Okay, it's like algebra on steroids, basically. All right, let's try the bottom two. Now, depending on your mathematical background, like who you've had as teachers in the past, I'm pretty sure some of you have seen this. Maybe you remember it, maybe you don't. I have heard some people refer to this as its name, which I was very impressed, by the way. Do we know what this is called? Who said it? Who? It is the difference quotient, okay? Very, very impressed with that. So the difference quotient is nothing too exciting. Okay, if you think about the word difference, that means subtraction. Notice how we're subtracting. And quotient means division. Notice how we're dividing. So mathematicians are not very creative people. If they name something, it basically is named what it should be, like difference quotient, right? So what we're going to do here is think about what this notation is telling us to do, very similarly to how we did the last one, and we're going to see what we get in the end. Now, this difference quotient is very, very important in calculus. Okay, we're actually going to be covering this today in AP Calc. There is a specific meaning behind what this represents for a function. Now, we're not going to talk about that meaning in here. Okay, that's what the calculus course is for. But what we can definitely do in pre-calculus, okay, is the algebra behind this difference quotient setup. So we're not going to discuss the meaning. We're just going to do the math behind it. Can we understand that? Okay, so it might not mean anything to you, but we should be able to do the algebra for it. All right, so if you take a look at the first term, we need g of x plus h. So very similar to how we did the previous one, like we plugged in x minus 2 into the f equation. For this one, we got to plug in x plus h for all the x's in the g equation. So let's just see what that first term might look like. So we'd have 5 minus 2, and then instead of the x, we want to plug in an x plus h, and then we're left with a minus 3. Let's clean that up. Okay, simplify it, make it a little bit better for us. We can distribute in the negative 2. And then combining like terms, looks like the 5 and the 6 can get us an 11, but that's about it. So right now, we know the first part of this difference quotient. We figured out the g of x plus h. We then want to take this answer we have, okay, that solution, and subtract the g of x equation from that. So let's go ahead and we'll just write down what we had previously. Okay, that was our answer to the first part. And we want to subtract the g of x original equation, the one that we have at the top. Again, if you're subtracting something, you're subtracting all of it. So we need to think about putting it in parentheses. All right. let's simplify that. We're breaking this difference quotient up into little pieces. Okay, we started with the first term, and now we're going to subtract the original function. We'll eventually divide by h, but let's not worry about that just yet. Let's go ahead and simplify, see what we have left. Let's see, parentheses come first. We have two pairs of parentheses, but we got to work on the inside one first. So we'll distribute in the -2. And then we'll get rid of the next parenthesis by distributing in the negative or the minus. Okay. So now that all the parentheses are gone, maybe we can start to combine some like terms like we did for the previous one. Do you notice anything that's going to happen? What do you see, Carter? Let's check it out. Okay, so -2x, +2x are gone. The numbers, we have 11 minus 5, which is 6, but then we have a -6, so all the numbers go away as well. So it looks like right now we figured out what the top part of that fraction should be. So after everything is said and done, the top simplifies to -2h. All right? So we just did the difference part of the difference quotient. We just took a look at the subtraction up top. We now have to remember that we have to divide by h. Okay, that's what the notation's telling us to do. So if we took this result from the top and divided by h, what are we going to be left with? 2, right? h's go away. So we're left with -2. It's a long process, but notice how we do get a simple answer. It might not be a number all the time. Okay, sometimes you might have a variable left. We'll see an example of that for this one, but we're going to break it up into easy, manageable pieces. Okay, just think about the first term. What does that represent? Then we can subtract the original function, see what we get, and bring in the division last. Okay, break it up into easy, manageable parts. We're going to try the same thing, the same difference quotient, but this time on the f function. So let's take a look at the first part here. Okay, we want to plug in x plus h in for every x in the f equation. So that would be the quadratic. For you procedural people, maybe you want to number these. I don't know if that would help. Okay, the first thing we did was figured out the x plus h value. Then we subtracted the original function on the end. And lastly, we divided by h. I don't know if that helps if you number them, but who knows. Okay, let's go ahead and clean this up. We're going to get rid of the parentheses. We're definitely going to have to go through a FOIL process because it's squared. So if you were to write x plus h twice and go through FOIL, we'd have firsts, outsides, insides, lasts. If we continue to simplify, working through, we can distribute in the minus sign, and then we have the +3. We still have parentheses, so we can keep distributing. 2x squared, 2xh, 2xh, 2h squared. And we'll have the rest. Okay. So now that all the parentheses are gone, can we start to combine some like terms? Do you see any? Go ahead, Hadley. Perfect. Okay, so xh, xh, those are the exact same variables, so they're like terms. 2 and 2 would give us 4. So we have 2x squared plus 4xh plus 2h squared minus x minus h plus 3. That's a lot, okay, but let's not forget what that represents. Okay, that is only the first term, okay, what we did for the f of x plus h. We then have to look at the notation. Okay, what is it asking us to do? Next comes the subtraction of the original equation. So whatever we have here, let's go ahead and subtract the original f of x. And that's at the top. Do you notice anything that's going to happen? We had a lot of things cancel out previously. Hopefully that happens again. Yeah.
2x squared cancel out.
Okay, positive 2x squared would cancel out with a negative 2x squared, so that's gone. Anything else? You see it? Yeah.
These are going to cancel out.
The 3's, good. Positive 3 would cancel out with a minus 3. Good. Yeah?
The x's are going to cancel out.
Negative x would cancel out with a positive x. Okay, after you distributed that minus in, it would change to a positive. So all those are gone. I think that's it, right? Everything else has an h in it. So we're left with 4xh plus 2h squared minus h. That's what the top is, okay, because that's the only part we've been working with so far. We then have to look at the notation and notice how we still have to divide by h. Bless you. Do you notice anything that can happen? Can we simplify a little further? You see it, Blair? Yeah.
Find out the h's.
Okay, so if you take a look at the top, notice how every single term has an h in common. We can factor that out, okay, pull it out of the top. So if we take an h out of every term, we're left with 4x plus 2h minus 1. Okay, that single h on the end, if you pull it out, you have a value of 1 placeholder. So if you pull an h out of everything, notice how that h would cancel out with the h on the bottom. So we're left with 4x plus 2h minus 1. There's our difference quotient result. Not as simple as negative 2, okay, like the previous one was, but it's still a result nonetheless. Okay, we followed what the notation was telling us to do. Like I said, these were a little involved, okay? They're processes. You have to take a look at the notation and ask yourself, what does it mean? The ones we do on the back, though, are not going to be as time-consuming, okay, or tedious, if you will. But these are very important in calculus. Again, we're going to be doing this today in the AP Calc class, but we're also going to be discussing what this answer means. Okay, so for right now, I'll just be happy if we can get here. Okay, we'll do baby steps. Okay, if we can get the result. Let's try some of the ones on the back. So, we have different functions at the top, and they're just going to ask us various different questions about how we can combine these functions together. If you take a look at A, we saw this notation yesterday, but we specifically had a number that we were substituting in. Notice how they want us to find an equation. Okay, so something with a variable that's left over. If you think about the way this notation worked yesterday, can we relate that or make a connection to how we could use it to find an equation? If you take a real hard look about how this is written, what does it look like we should do? What do you think, Travis?
Put the h of x equation in the x spot for g of x.
There we go. Notice how h of x is inside the g function. So we're going to literally take the h equation and plug it into the g function, okay, the g equation. So 1 minus 2, and then instead of the x, we're going to plug in the h equation. From there, we're going to simplify. Use some algebra to make it nicer. We can distribute in the negative 2, so we get negative 3x plus 4. And then if all the parentheses are gone, combine some like terms, we'll get negative 3x plus 5. Okay, not as bad as the difference quotient, but still the same principle. Okay, we're plugging in expressions now instead of numbers. let's see. Do you guys think you can try B? Try the next one. All right, if you take a look at the way it's written, it looks like the F equation is inside the G equation. So that's what we're literally going to do. We'll take the F equation and plug it in to G. Doing so, you can distribute, combine some like terms. In the end, we get 2x squared minus 6x plus 11. How'd you do? Good? All right, let's try the next one. Looking at the notation, it literally looks like the G is inside the F. So we're going to take the G equation and substitute it in for the F. Now, I think this one's going to be a little good because we have two places to substitute it in for, and we have a power of 2. All right, let's clean it up. So, order of operations, parentheses and exponents come first. Let's take a look at that first term. So if it's squared, you got to think about writing it twice, maybe actually write it if you have to, and go through a FOIL process. So we'll have firsts, outsides, insides, and then lasts. We need negative 2x times a negative 2x. So it'd be a positive 4x squared. Okay, that's just the parenthesis and the exponent, order of operations. We can continue to work through. Maybe we can distribute again. We do have parentheses left, however, so another distribution is going to be necessary. And now that all the parentheses are gone, we'll combine some like terms. So let's see, negative 4x squared. That's the only x squared term. X's, we have 2, 2, and negative 6. So altogether, that's negative 2. And then for the numbers, negative 1 plus 3 is 2, minus 5 would give us a negative 3. Okay, there's our equation. We can leave it like that. I know some of you might see the power of 2 and think, oh, I need to factor that. Okay, but don't feel like that's necessary because it just wanted an equation. Okay, you can leave it like that. Factoring is not always a necessary step. Do you guys think you can try D? Try that one. All right, so when I did D, I got negative 2x plus 3 over negative 2x minus 2. My question is, do I leave it like that or can I keep going? I'm wondering if I have a negative 2x up top and a negative 2x on the bottom, I can cancel those out. Can I do that? One's up top, one's on the bottom. Can I cancel them? What do you think, Maggie?
Because you're adding stuff to it.
You're adding or subtracting, right. Okay, so, love it. When you are adding or subtracting terms in a fraction, you cannot simply choose willy-nilly what you want to divide or cancel out. Okay, and take a look why. I'm going to use a number example. If I did negative 2 plus 3 over negative 2 minus 2, okay, the tops would simplify to 1, the bottoms simplify to negative 4. Okay, so I know my answer should be 1 over negative 4. If I choose to cancel, because I see one's up top, one's on the bottom, notice how I'm left with 3 over negative 2. And that is not what we know the answer should be. So if you're adding or subtracting, you cannot cancel things out. When can you cancel things out? Yeah? When you're multiplying. Okay, so if I change this to negative 2 times 3 over negative 2 times negative 2, that would be negative 6 over 4, which simplifies to negative 3 over 2. Notice how if I cancel out the negative 2 on top and bottom, that's what I still have left. Okay, so if you're adding or subtracting, you can't just choose what you cancel and when. Yes?
Could you like take out a negative from all the terms there? And, like, how many-
Yes. Okay, so try this. If you take a negative out of the top, if you want to do this, you could leave it like this definitely. But if you chose to go that route, take a negative out of the top. This would be 2x minus 3. Take a negative out of the bottom, 2x plus 2. Now you're multiplying things together, so those could cancel. So you could leave it like that if you prefer. Okay, but either one is fine. Do we understand when we can cancel things and when we cannot? Okay. I bet I'll see it at some point this year, okay, and again, that's okay, but we need to make sure that we start to be aware of when we can and when we can't do mathematical operations. All right, good. Let's try E. A little different for this one. Find the equation for that notation. Again, take a hard look at it. What does it look like it's asking you to do? We initially see a negative 6x, and then it says times h of x. So we're going to multiply by the h of x equation. If we continue to look at the notation, it says to subtract f of x, but if we're going to subtract a function, make sure you put it in parentheses because you need to subtract the whole thing. You're subtracting every single part of it. All right, from there is algebra, distribution, combining like terms, see what we have left. So let's try the first one. Negative 6x into everything, we'll get negative 9x squared plus 12x. And then for the next parenthesis grouping, distribute in the minus sign. All the parentheses are gone, so we'll combine some like terms. Negative 8x squared plus 9x plus 5. Okay. We doing okay? Hanging in there? I think we'll be able to get this last one in before the bell rings, okay? Well, we're going to skip over to I, okay, the big box on the right-hand side. For which values of x is f of x equal to g of x? What is that notation asking us to do or asking us to find? If two equations are equal to each other, yeah? Graphically, we're finding intersection points, okay? But notice how we don't have a graph to actually analyze, but we do have their equations. So let's see if we can figure out the intersection points based off of that information. So the f equation was at the top. And we're going to set that equal to the g equation. Where do you want to go from there? Go ahead, Hadley.
Maybe combine like terms by moving the g of x over some equal to 0.
Sure. Okay, so you can move all the right terms to the left or all the left to the right. We want to set it equal to 0 because that power of 2 is a little light bulb saying factor, factor, factor to help you solve it. So if we move them over, we'll have a plus 5x and a minus 6. Where do you want to go from there? Pull out a negative. I like it. That'll help us factor a little easier. Two numbers that multiply to a positive 6 but add to a negative 5. Yes?
-1 instead.
Those add to negative 5, but if you multiply those together, this would be negative. So it works for one, but not for both. Is there another set? Yeah? -2, -3. Good. 6 and 5 are the tricky numbers because the factors of 6, like 1 and 6 and 2 and 3, can get to 5 somehow. So those are tricky. You got to figure out which pair it would be. I like -2 and -3. So what are the intersection points? Where would these two graphs cross if we actually had the picture of it? 3 and 2. Good. All right, I like it. We'll go ahead and pick up with F and J tomorrow just as practice, and then we'll start the last section of our unit.